The Columbia River Gorge showcases some of the Northwest's most astounding geology. From Cascade volcanoes that erupted 30 million years ago and still continue today, to Ice Age floods that swept through the landscape only 15,000 years ago, this is a place that records the history of the Northwest. We're going to focus on the Columbia River basalts, lava flows that blanketed the Northwest and form most of the walls of the gorge. Some of the gorge's most important geology is found in the dark brown lava flows that form these walls. These rocks are basalts. They were once torrid, fast-moving lava flows that erupted from fissures in eastern Oregon, eastern Washington, and even Idaho, and flowed all the way to the Pacific. They're some of the longest and most extensive lava flows on the planet, and geologists today are still studying them. These basalt flows are named after the river that exposes them so well. Collectively, they're called the Columbia River basalts. And almost every layer in the gorge walls is a different basalt flow. Here at the Rowena Plateau, you can see behind me a great thickness of Columbia River basalts, about 1,000 feet of basalt flows altogether. Columbia River basalts erupted for about 10 million years total, from 17 million years ago until about 6 million years ago. These basalt flows produced enough basaltic lava to build a road from the Earth to the Moon, a 1/4 mile wide and 100 feet thick. Put another way, that's 63,000 cubic miles of basalt. Now, this didn't happen all at once. These flows erupted in 4 discrete episodes. The oldest are called the Imnaha. The next are the Ronde basalts that are the most voluminous. Then there's the Wanapum basalts that are found really around the Dalles and sort of central Washington. And finally, the Saddle Mountains basalts, which are the last squeezings of the basalt flows, but also include the longest basalt flow on the planet. So the Columbia River basalts are a great example of a large igneous province, what geologists would call a lip. And behind me at Rowena, you see an excellent example of why they're such a world-renowned igneous province. The Columbia River basalts and related basalts cover much of eastern Oregon and Washington. Geologists divide them into 2 separate groups of basalts, the Steens basalts and the Columbia River basalts. The Steens covered much of southeast Oregon. The Columbia River basalts, of course, cover the Columbia Plateau and much of central and eastern Oregon. There were hundreds and maybe even thousands of lava flows. They're divided by their age and compositions into 5 major groups, the Steens, and then 4 separate groups of Columbia River basalts, the Imnaha, the Grand Ronde, the Wanapum, and the Saddle Mountain basalts. The earliest of the Columbia River basalts are called the Steens. They erupted near Steens Mountain, or what's now Steens Mountain and then was a flat plateau, about 17 million years ago. This eruption really marked the inception of the Yellowstone hotspot, the first time it reached the surface. The same lavas, the same hotspot, today power Yellowstone. The next pulse of eruptions, 17 to perhaps 16.5 million years ago, are part of the Columbia River group. They're called the Imnaha basalts, and they erupted near the junction of Oregon, Washington, and Idaho. They're not very voluminous basalts. They didn't get very far. They sort of puddled near that, what today is that border. Neither the Steens nor the Imnaha basalts appear anywhere in the Columbia River Gorge. But things changed drastically about 16 million years ago. There were huge volumes of basalts, including some of the largest lava flows ever seen or known on the planet. These lava flows began erupting about 16 million years ago and may have erupted in a mere 500,000 years or 250,000 years and covered most of what's now the Columbia Plateau in hundreds of thick lava flows. These flows are known as the Ronde flows. They're named after exposures along the Ronde River in northeast Oregon that's not far from their vent area, mostly in the Wallowa Mountains and in the Chief Joseph Swarm. They're also well exposed in the Columbia River Gorge. Let's take a look at one. Many of these voluminous Ronde flows are really quite thick. Most display some kind of columnar jointing. Columnar jointing, or columns, form as this basalt lava cools. The top of the basalt flow is exposed to air, and it chills pretty fast. The lava solidifies quickly, and it contracts into columns, not dissimilar from the process of making mud cracks as mud shrinks. Geologists call the smaller upper columns that form really fast an entablature. Many of these small columns are curved and irregular. The bottom of the lava flow, though, is often insulated by the ground. It cools and solidifies much more slowly than the top, and so columnar joints in the bottom of a lava flow take their time forming. And they tend to be larger. They tend to be more regular. Geologists call this bottom part of the flow with bigger regular columns the colonnade. One way of distinguishing among a lot of very similar looking Ronde flows is by their magnetic polarity. Basalt flows contain tiny crystals of iron oxides, and as the flow cools and solidifies, these tiny minerals, iron oxides, like magnetite, align themselves with the Earth's magnetic field. They're kind of like tiny compass needles. But the Earth's magnetic field isn't stable. It changes over geologic time, and it flip-flops. Not the whole planet, just the magnetic field. So by taking a very accurate core that's oriented from a basalt flow and measuring the orientation of those tiny compass needles, the iron oxides, in this chunk of basalt, geologists can determine whether this flow was erupted as a normally polarized flow with the north magnetic pole where it is today, or as a reversed magnetic flow where the north magnetic pole is actually at the south geographic pole. That's one way of determining where you are in this huge sequence of Ronde basalt flows, determining whether they're normally or reversely magnetized. We're here in the gorge looking at the Ronde basalts. These thick basalt flows began erupting about 16 million years ago from vents in eastern Oregon, eastern Washington, and parts of Idaho. They're named the Ronde basalts for their deep exposures along the Ronde River. And as you can see here, they're very thick basalts. They're among the greatest of all flood basalts. And these flows extend from eastern Oregon all the way to the Oregon coast, where they form Saddle Mountain, Seal Rocks, and other promontories on Oregon's coast. They're fine-grained basalts, and they contain more silica and iron than many of the other Columbia River basalts. The Ronde basalts, like all basalts, are dark on a really fresh surface, and they're a brown color on a weathered surface due to the oxidation that happens as water encounters all the iron in this rock. The Ronde are typically fine-grained, so let's see exactly how fine-grained they are. So in a Ronde basalt, there's really practically no large crystals that you can see. It's a very dark, plain matrix. And that's one of the things that distinguish these basalts. So that it's very hard to tell one Grand Ronde flow from another. We often have to go to other techniques, chemical analysis, and also using the magnetic stratigraphy, or whether this is a reversed or normally polarized flow, to determine where we are in the Grand Ronde section. About 14.5 million years ago, a new burst of basalts reached the surface. They're called the Wanapum basalts, and they erupted from linear vents in eastern Oregon, eastern Washington, and Idaho. They're really well exposed here at Columbia Hills State Park in Washington. This is the Priest Rapids flow. It kept encountering problems on its way down the Columbia River channel. Its lavas blocked the channel, and then the back part of the flow encountered a lake. When these lavas flowed into the lake, instead of forming columns, they formed round, interesting-looking forms called pillows. Here in the Dalles, we see the bottom of the Priest Rapids flow. You can see the pillows in it where the Columbia River basalts, the Priest Rapid flow, ran into water, and as a result chilled into rounded forms called pillows, and ash and explosive chunks of basalt. It's called Palagonite. It's the yellow material around those pillows. Here, the Priest Rapids flow ran into a lake that the front part of the flow created by blocking the Columbia River near Mosier. As the flow entered the lake, it began to fill it up. And gradually, the basalt found itself running over not lake water anymore, but solid ground that the basalt itself made. So the basalt then began to cool not as rounded pillows, but as columnar joints. It's much more normal basalt that we see on the top. This is one of the pillows in the Priest Rapids flow. And you can see a lot of diagnostic features of pillow lavas here. For one thing, pillow lavas are rounded. That's why we call them pillow lavas, where they chilled in cold water when they entered the water. Second of all, they have a glassy rim. And this glassy rim is formed as the basalt outside of the basalt chills instantaneously into a glass as it enters this now boiling water. Most pillow lavas or pillow basalts, most pillows, have radial joints that radiate from the center towards the outside, and these form as the lava cools gradually towards the inside. Another real common feature of pillow lavas is this yellow material that's around the outside of the pillow and forms a matrix. This is called Palagonite. Palagonite is composed of ash from the eruption, ash and small particles of basalt that are broken as the lava chills and then explodes, and sometimes sediment that might be in the lake and certainly in the ocean bottom where the pillow is forming and where all of the steam and turmoil from this eruption churns up some of that lake sediment. Palagonite is very fragile, and it tends to leave the pillows sticking out of it a bit most of the time. But it's a real characteristic of pillow lavas. We find angular chunks of basalt sometimes in these pillow lavas that are called pepperite, where the basalt never really was fluid enough to make an elongate pillow, but instead exploded, creating a very angular fragment. So pillow lavas are a really distinctive form of basalt, and they're found in the gorge in a number of places. The most stunning example is here in the Dalles, at the bottom of the Priest Rapids flow. We find them also at Crown Point, part of the upper flow at Multnomah Falls, and many other places in the gorge. This is the Rasa Flow. It's a massive and very fluid basalt flow, 14.6 million years, that flowed across central Washington and into the Columbia River Gorge. Kathy Cashman at the University of Oregon has calculated that it moved at about 15 miles an hour in places. It's one of the Wanapum basalts, and it's a basalt flow that's distinguished by having large plagioclase crystals in it, whereas the overlying and underlying flows don't. So let's take a look and see if we can find those large plagioclase crystals. Here they are, and they distinguish the Rasa flow from the ginkgo flow underneath it and the Priest Rapids flow above it that simply don't have any large crystals or phenocrysts, visible crystals, as geologists would call them. The Pomona Flow is part of the Saddle Mountains basalts. It's 12 million years old. It has thin, what are called Hackley joints, that distinguish it from many other Columbia River basalt units. And that's important because the Pomona Flow is the longest basalt flow known on the planet, with one possible exception in India. This lava flow originated near Orofino, Idaho, and it flowed 400 miles to the Pacific Ocean. You see it here at Mosier, and if you go to Astoria and a place called Pack Saddle Mountain and Radar Mountain on the Washington coast, you'll find exactly the same basalt flow. The Pomona Flow is a fine-grained flow. It has very few crystals in it, and that also helps distinguish it from other lava flows in the Columbia River basalt group. So the Pomona Flow, longest flow on the planet, you can put your hand on it right here at Mosier. By 6 million years ago, the eruptions of Columbia River basalt ended. The last eruptions were mere dribbles compared to the huge volumes of basalt erupted by Grande, Ronde, and Wanapum flows. But the hotspot that produced the Columbia River basalts is still alive today. We know it as Yellowstone, and it's due to erupt sometime soon. So the Columbia River Gorge is an important place to learn about the Columbia River basalts, world-class lavas that erupted 17 to about 6 million years ago. They covered much of the Columbia Plateau, in fact most of the Columbia Plateau, in hundreds of basalt flows that are a total of 3 miles in thickness beneath Tri-Cities, Washington, and almost a mile thick near Dog Mountain in the gorge. These basalts, the Columbia River basalts, erupted in 4 major pulses, each lasting a very long time, although the Grande Ronde basalts, the biggest of all of these eruptions, may have erupted in 250,000 years. The Grande Ronde basalts are the most voluminous, and in the gorge they're really most accessible at Multnomah Falls. They erupted in northeast Oregon, flowed all the way to the coast. Saddle Mountain and parts of Tillamook Head are the distal or far end of these Grande Ronde basalt flows. Then there was the Wanapum basalts, for about 14.5 million years ago to around 12 million years ago. They're easy to find in the gorge, especially in the eastern end from the Dalles to Hood River. They include the Priest Rapids flow and its pillow lavas. They're so well exposed near the Dalles. The ginkgo flow that comprises both Haystack Rock and Yaquina Head on Oregon's coast, but erupted from eastern Oregon. Then there's the Pomona Flow, the longest known basalt flow on Earth, 12 million years old, that erupted in Idaho and flowed all the way to the Washington coast. So the Columbia River basalts are really an incredible legacy. If you think of these basalts as hot lavas or boiling, explosive interactions between lava and river, geology can bring the somber walls of the gorge to life. Almost 11 million years separate the time that the last basalt lava followed the Columbia's channel until the Ice Age floods ripped through the landscape less than 1 million years ago. Between the basalt lavas and the Ice Age floods, entire cascade volcanoes were born and eroded away. Intrusions like Wind Mountain invaded the solid pile of basalts, cooled, and were revealed by erosion. And other volcanoes, including the Underwood Volcano and Haystack Butte, ran their entire life cycle. The Columbia River basalts, in all of their forms and all of the flows, are one of the true treasures of the Columbia River Gorge. And they're a treasure that scientists and research are teaching us more about every day.